Okay, so welcome again to the course Fundamentals of Solar Photovoltaics and Technologies. So in this new lecture we will today talk about intrinsic and extrinsic semiconductors, whose discussion we did start in the last lecture but couldn't complete it. So just to recap, the intrinsic semiconductars are basically pure semiconductors with no intentional addition of impurities. So examples could be silicon, gallium arsenide and many other semiconductors. So they may have impurities, but those impurities are unintentional in very small amounts, and these are made using certain processes which are very energy intensive and time intensive in nature, which we will discuss in the later lectures. The carrier concentrations in semiconductors are defined as Ne and Nh. Ne is the electron concentration in the conduction band and Nh is the whole concentration in the valence band, and this is nothing but product of probability of occupation multiplied by density of states within the band of energy range EC to infinity, and same is for hole within the range minus infinity to EV, and the whole probability is 1 minus Fe, which is multiplied by density of states in the valence band. So all you can do is that in the DE you can add V here in the valence band and C here in the conduction band, and that will give you expressions for electron and hole concentrations, which are for electron Nc into exponential EF minus EC by kBt, and for holes it is Nv into exponential EV minus EF divided by kBt. Since in an intrinsic semiconductor Ne is equal to Nh, we can write this Ne into Nh will always be equal to Ni square. Okay, and from this we can also write Ne is equal to Nh is equal to Ni is equal to square root of Nc Nv into exponential of minus Eg divided by 2 kT. Nc and Nv are basically effective density of states in conduction and valence band respectively. We also saw that the Fermi level in a pure semiconductor is at 0 Kelvin is in the mid gap position. So if you have a conduction band and valence band like this, EC and EV, then Fermi level will lie right at the point, you can say Eg divided by 2 and Eg divided by 2 from the both sides at 0 Kelvin, and this does move with temperature. Another important point that we saw was that the conductivity of undoped semiconductor sigma is equal to basically NEE mu E plus NH E mu H, and given that electron concentration or hole concentrations, they have strong dependence on exponential dependence on energy gap and temperature. So sigma happens to be more or less dependent upon band gap and temperature. So this is the reason why conductivity in intrinsic semiconductors, if you plot now ln sigma as a function of 1 over T, you will see that there is exponential variation, the slope being minus Eg by 2 kb, and this explains why we have a different conductivity behavior, resistivity behavior in semiconductors as a function of temperature in comparison to metals, which show a decrease in conductivity as temperature increases, whereas converse is observed in case of semiconductors. And so in case of metals, the decrease in conductivity is governed by scattering of electrons, and that scattering leads to reduced mean free path, as a result reduced mobility, and hence you have lower conductivity as a function of temperature, which could be because of defects or because of temperature, because of vacancies also. But in case of semiconductors, the increase in conductivity as a function of temperature, with increasing temperature, is primarily governed by the increase in carrier concentration as the temperature increases. So both Ne and Nh increase as temperature goes up, which means conductivity also goes up as temperature increases. So these were some main conclusions that we drew in the previous lecture. Now let us look at this particular lecture, and this if you compare the properties of different semiconductors, semiconductors as we saw are not necessarily group 4 semiconductors, but they can also be combinations of group 3 and group 5, and it could also be combination of group 2 and group 6. So, if we plot 3 key properties, that is melting point, energy gap and lattice parameters, what we see is that as you go down the column, as the column descends, what we see is that both melting point and band gap decrease and lattice parameter increases. And this is understandable because as you go to as you go down the column, the bonding becomes weaker, as a result your melting point and band gap decrease. And as you move away from group 4 to group 3,5 to group 2,6, you can see that. So, here you can see, for example, for group 4 the blue ones, the first thing. So, as you go down from diamond to silicon to germanium, you can see that the band gap has dropped significantly. Similarly, the melting point has also dropped significantly and lattice parameter has increased significantly because atoms become bigger and they have lot many electrons. As a result, there is more repulsion between the atoms. And in comparison, if you go horizontally across the row from group 4 to 3,5 to 2,6, what we see is that because as you go from 2 to 3,5 to 2,6, your bonding become more and more ionic as compared to covalent. So, your ionic character increases, and ionic bonding is generally more stronger than covalent bonding. As a result, you see that as you go horizontally across the rows, you see that there is increase in melting point as well as increase in the band gap, and correspondingly there is a slight decrease in the lattice parameter that we observe. So, that is a conclusion, that is a nice observation that you can make by looking at the periodic table, mixing the elements together and just looking at the bonding and correlating it with key properties like melting point and energy gap. So, if you look at the periodic table and especially the important part of periodic table, that is group 4, let me just draw that. So, if you look at the right side of periodic table, and we are going to draw only group. So, we can say here we have group 3, then we have group 4, then we have group 5, and then we have group 6. We can forget about the rest. So, we start with first boron, carbon, nitrogen, oxygen. Boron is 3, carbon is boron is 5, carbon is 6, nitrogen is 7, oxygen is 8. And then we go to the next row, that is aluminum. Aluminum is 13, silicon is 14, then we have phosphorus which is 15, and then we have sulfur which is 16. And if you go to next row, then we have gallium, we have germanium, we have arsenic, we have selenium, and the next row will have indium, tin, antimony, tellurium, and then thallium, lead, bismuth and polonium. So, let us just focus on these these 4 columns. So, here the important ones that we consider for semiconductors are, so we can just write the numbers 31, 32, 33, 34, and for this we can write 49, 50, 51, 52, and here we can write 81, 82, 83 and 84. Generally, the elements that we consider in case of semiconductors are the ones these are the ones we consider for semiconductors within the blue box. You can say. So, we can see that first of all in group 4 what we have is silicon. Silicon is a group 4 semiconductor, and then we can mix these aluminum phosphorus, we can mix these, and we can, well, I mean you go to very low melting point, so it does not make any. You can also mix group 2. So, group 2 on this side will be, so group 2 will be on the side of gallium, it would be zinc, then we have here cadmium, and we have mercury, we do not have to worry about mercury. So, zinc is 30 and cadmium is 48, and you can also mix these zinc with sulfur, zinc with oxygen, cadmium with sulfur, cadmium with oxygen, zinc with selenium, cadmium with selenium, cadmium with tellurium. So, these mixings can be done. Now, the important point here is that silicon being a pure semiconductor, it can be mixed with elements either from group 3 or from group 5. When you do that, you change the properties of these semiconductors. So, silicon being group 4, so silicon being group 4, if you add elements from group 3 or from group 5, they bring different number of electrons to silicon. As a result, it changes the electronic character of silicon. How it does that, let us see. So, when we mix these atoms from group 3 and group 5 in silicon, what we form is a semiconductor which is called as extrinsic semiconductor, or rather we can say it is intentionally impure semiconductor. So, we add impurities intentionally and certain types of impurities, and these impurities are substitutional impurities. So, if you have lattice of silicon like this, so if you have lattice of silicon, so silicon is bonded with 4 neighbors, then let us say these are all silicon atoms. And we replace some of these sites with another atom. So, this site if I replace it for an atom, let us say a boron atom or a phosphorus atom, this is called a substitutional atom. It substitutes silicon on its lattice. So, doped, basically what we are, this process is called as doping. When we add impurities in a smaller amount such as ppm level, parts per million level at the substitutional sites, this is doping of substitutional impurities in silicon lattice at the level of ppm. The properties are dictated by the amount of impurity that we add. So, impurity concentration, how much impurity are we adding to the semiconductor will dictate the properties such as electronic conductivity, electrical conductivity, mobility, electron carrier concentration, all of these things are affected by the amount of impurity that we add. Third is when we add dopant with a valency of more than 4, we create what we call as an N-type material. So, if you look at dopant with valency of 4 plus, which means we have nitrogen, we have phosphorus, we have arsenic, we have antimony, we have bismuth. So, when we add these elements to silicon, typically we add nitrogen or phosphorus or arsenic. When we add these elements to silicon, these are all plus 5 elements, we create an N-type material, that is N-type silicon, which will have number of electrons much higher than number of holes. Conversely, if we dope silicon with an element of valency which is less than 4, that is either boron or aluminum or gallium, one of these elements, then we create a p-type silicon or p-type material, which will have higher hole concentration as compared to, significantly higher hole concentration as compared to electrons. So, this semiconductor which is doped with substitutional impurities in levels of the order of ppm or around that is called as an extrinsic semiconductor. So, we first have what we call as N-type semiconductor. So, N-type semiconductor will be something like that. So, we have silicon, some of these silicon atoms are replaced by, let us say, antimony. So, this is antimony, rest is all silicon, let us say these are all silicon. So, what it does is, so you have a bonding between these atoms, these are all tetrahedrally coordinated bonds, which means your coordination number is 4. Each atom will have 4 nearest neighbors. So, when you put antimony, antimony occupies the substitution interstices in the silicon lattice. It could be arsenic, it could be phosphorus also. Antimony brings with itself 5 valence electrons. So, antimony will arsenic or antimony or phosphorus will bring 5 valence electrons. 4 of these will be used in bonding with silicon. So, 4 of these 1, 2, 3, 4. So, 1 here, so 1 will be here, 1 will be here, 1 will be here, 1 will be here. 1 is loose. So, this is your loosely bound, and this provides an extra electron to silicon. So, extra electron to silicon. So, it is like impurity donating an extra electron to silicon. That is why these elements, which are +5 elements, they are called as donors, okay? And these electrons are the donated electrons. Essentially, in terms of energy landscape, what it means is if this is your EC, this is your EV, then you create an extra electron by donation from, so this is the extra electron, and this comes by the fact that impurity has an energy level ED, this is donor level. This lies very, very close to the conduction band, and this extra electron is able to go from donor level to the conduction band edge, and this creates an excess of electrons in the n-type semiconductor. Conversely, in case of a p-type semiconductor, we use a dopant like boron, aluminum, indium, which again occupy the substitution positions. So, if we now draw the lattice of silicon, so these are all silicon atoms. Some of these silicon atoms will be occupied by things like boron. Now, again we have the bonding here. So, we will have covalent bonds with the nearest neighbors. And now what we will have is we will be short of, so one electron is with this, but there is no electron here. So, this is no electron, boron does not have an extra electron. So, this electron then is contributed by an electron from one silicon atom, and as a result what we form an empty state in silicon, and this empty state in silicon is basically constituted as a whole. So, what it means is that if you have conduction band edge here, valence band edge here, and this is the boron energy level, let us say this is for boron. So, the one electron from valence band of silicon goes to the energy level of boron. So, this goes here, it creates a hole here, okay. And this means boron has accepted one electron from silicon, and that is why this is called as an acceptor atom. And as a result, every boron atom, if it is fully accepting, then it creates one hole, which means if you put in lot of boron atoms, you will have lot of holes in the silicon. So, this is such kind of material is called as p-type silicon or semiconductor. This will be dominated by an excess of holes. So, this will create a hole in the valence band, and this will create conduction in the electron in the conduction band. So, this will be electron in the conduction band, and this will be hole in the valence band. So, basically if you look at this now, intrinsic semiconductor is pure, it has no intentional impurities, just like pure silicon. Number of electron is equal to number of holes, that is Ne is equal to NH is equal to Ni, and Ne and NH are given by these expressions which are shown in this here that we derived earlier. Extrinsic semiconductor on the other hand is a semiconductor which is intentionally doped with impurities, which does not have equal number of electrons as compared to equal number of holes, which means Ne is not equal to NH. So, for a p type, which means silicon doped with boron, it will have Ne greater than NH, NH greater than Ne, and for N type silicon doped with, let us say, phosphorus, in this case Ne will be much larger than NH. But one thing that you must remember that must always happen in these semiconductors is whether it is, there is a law called as law of mass action, which is basically from mass conservation. For both intrinsic and extrinsic semiconductors, when they are under thermal equilibrium, the product of Ne and NH must always be equal to Ni square. So basically, even though N type semiconductor or P type semiconductor may have a large number of electrons, its product with Ne dot NH must always be equal to Ni square, which means that Ni square equality is always to be maintained. So you will form, so all the thermally created holes or electrons in these domed semiconductor will then recombine. As a result, your whole electron concentration will go down in case of N type or P type semiconductors respectively. So this is something that is true for every type of semiconductor. So basically we can explain this in the form of energetics. So basically silicon is, let's take the example of N type semiconductor, which is antimony doped silicon. Antimony is a donor impurity. We know that binding energy of an electron, for example, in a hydrogen atom is given as Eb is equal to minus me to the power 4 8 epsilon square r square. You can put a minus here, of course, I mean it's basically minus 13.6 eV. Now if you for a silicon atom, we understand that epsilon r is 11.9, me star is 0.26, the free mass of electron. Then we can do this binding energy for silicon atom as being 0.032 electron volt, which if we are able to overcome this much energy using thermal energy, in case of binding energy, this is a calculation with respect to antimony. So this amount of energy will be different for different elements. So for antimony, this binding energy turns out to be 0.032 electron volt, which is much smaller than the thermal energy, because thermal energy 3 kT is about 78 milli electron volt, which means all the electrons which are present with impurity atom can be transferred into the conduction band. Energetically, what it means is that if you have this is as EC and this is as EV, then donor atom creates an energy level here. This is the difference EC minus ED, and this is smaller than 3 kT, which means every free electron which is here, extra electron, they will all be able to be excited. If you are able to excite all the electrons from donor to conduction band, donor level to conduction band, in that case number of donor atoms is equal to number of electrons that you contribute. So if you have 10 to the power 18 donor atoms Nd per centimeter cube, then Ne will also be equal to Nd, which will be equal to 10 to the power 18 per centimeter cube. This is much larger than your intrinsic carrier density, by the way. Intrinsic carrier density is 10 to the power 10. So this is 8 orders of magnitude higher. So Ne in this case will be much larger than whole. So Ne of the order of 10 to the power 18 per centimeter cube is much larger than the whole carriers. So these are called as majority carriers and these are called as minority carriers. Okay. In a pure semiconductor there is no minority and majority, but in an impure semiconductor you will have a majority or minority carrier depending upon the type of atom. Similarly, for a p type semiconductor, if you add a lot of dopant elements, the impurity concentration is equal to the hole concentration, and hole concentration is much larger than electron concentration. So for a p type semiconductor, you will create energy level somewhere here. This is EA, and if it is close enough, then electrons here will be able to get excited to the acceptor level, all of them. So this will create electron here, and these will leave hole in the valence band. So, which means here, so in this case you can write Na is equal to Nh, in the previous case you can write Nd is equal to Ne. So, this is for p type and this is for n type, all right. So, it is important to have the energy levels of donor and acceptor atoms close to conduction or valence band for an n type or p type semiconductor. So, basically you can calculate these energy levels. If you look at these impurities, tin, phosphorus, arsenic with antimony, phosphorus, arsenic with respect to germanium and silicon, these are the energy levels. These are all in so these are ionization energies for different atoms in silicon or germanium. So, for silicon you can see that antimony has 0.0039, phosphorus has 0.045 and arsenic has 0.049. I think we have added just one extra 0 here, it should be 1 0 here. And for acceptor atoms these energies are a little bit higher, but again you can see gallium, boron, aluminum has much lower energies than 3 kT. So, these elements like boron, aluminum or phosphorus, arsenic or antimony, if you dope them, you are basically convert all the extra electrons into donor electrons or conduction electrons in case of n type semiconductor, and you are able to create as many number of holes in case of a p type dopant in silicon. So, but when you form these, when you put these element now, so what you have 4 entities. First entity is donor atom. So, donor atom is positively charged. So, you can say this is Nd plus because it is positively it is positively ionized, it has donated 1. Acceptor atom can be written as negatively charged, which means it will be Na minus. In addition we have electrons which are Ne, and these are negatively charged particles, and we have holes which are Nh, and these are positively charged particles. For a solid to be at thermal equilibrium, solid must be charge neutral. No matter what you have created, what you have added, solid must always be charge neutral. So, when it is in a state of equilibrium, we can write this charge neutrality equation, that is Q multiplied by all the positive charges minus all the negative charges must be equal to 0, which means plus all the negative charges must be equal to 0, which means net charge must be equal to 0. So, Nh minus Ne plus Nd plus minus Na minus should always be equal to 0 multiplied by Q, and we can also write Nh, the equality that Ne dot Nh must be equal to Ni square. So, we can say that Nh is equal to Ni square divided by Ne. If we substitute this in the previous equation, we can write a quadratic equation here and we can solve it for Ne and Nh. It turns out Ne will be equal to Nd minus Na divided by 2 plus Nd minus Na square divided by 4 plus Ni square to the power 1.5, and same for Nh. And if we say that Nd is much larger than Na for an n type semiconductor, we can, and as well as Ni, we can write safely that Ne is equal to Nd and Nh is equal to Ni square divided by Nd. Similarly, for a p type, if Na is much larger than Nd, then we can say, as well as Ni, then we can say Nh is equal to Na and Ne is equal to Ni square divided by Na. So, these are very important conclusions that we make by charge neutrality. For an n type, Ne is equal to Nd plus, let us say, all the ionized atoms, and Nh will be equal to Ni square divided by Nd. And for a p type, Nh is equal to Na plus and Ne will be equal to Ni square divided by, and here we can say Ne is much larger than Nh and here Ne is much smaller than Nh. So, these are two conclusions that we draw from these equations. Another thing that we want to see is that when you dope these semiconductors, they also change their Fermi level. What is observed is the Fermi level for n type material, you can also calculate it, that the Fermi level which is normally at the mid gap position, it tends to shift towards the conduction band for a n-type material and it tends to shift down for a p-type material. Let us see how does this happen. So, in the previous class we wrote the equations for Ne and Nh in the form of in terms of Ni, Ef and EFi. So, now since these are extrinsic semiconductors, so n-type semiconductor, so n-type semiconductor will have a Fermi level which is called as EFn, and p-type semiconductor will have a Fermi level which can be depicted as EFp. Okay. So, Ne, it was written in terms of Ni and difference of real Ef minus the intrinsic Ef divided by Kt, that we did in the last class. Similarly, we can write Nh is equal to Ni into exponential of EFi minus Ef divided by Kt. Now, we know that from this we can work out, if you take the log on the other side, we can write this as Ne divided by Ni log of ln Ef, let us say this is for Ni conductor, EFi divided by KBT, and for a n-type semiconductor Ne is equal to Nd. So, I can write this EFn minus EFi being equal to KBT into ln of Nd divided by Ni. Similarly, if you do the same exercise for a p-type semiconductor using this equation, I can write EFi minus EFp, this will be equal to KBT ln of Na over Ni, and this is what it is written here. For a Fermi level of a n-type semiconductor will be given that Nd is much larger than Na and it is equal to and as well as Ni, then we can write EFn minus EFi is equal to KBT plus into Na ln of Nd divided by Ni, which means EFn will be equal to EFi plus KT ln Nd by Ni. So, it will go up. So, this goes up. Here EFp will be equal to EFi minus of KT ln Na over Ni, which means it goes down with respect to the mid gap position. And for a p-type semiconductor, Na must be much larger than Nd and Ni both. So, basically to summarize, and also another thing is that if you keep doping, what will happen? If you keep doping it, then Fermi level goes very close to conduction and very close to valence band for very, very high doping levels. So, very high doping Fermi level is very close to EC or EV depending upon type of doping. So, that is where now we distinguish between a semiconductor which is degenerate and which is a non-degenerate. So, if the semiconductor lies, so this energy level will be EC minus 3 kT and this will be EV plus 3 kT. So, if the Fermi level lies within this range, that is EC minus 3 kT to EV plus 3 kT, then this semiconductor is called as non-degenerate semiconductor, which means it will act like a semiconductor. Okay. The moment it crosses this barrier of EC minus 3 kT here or EV plus 3 kT here. So, this will happen upon n-type doping, excess, and this is excess p-type. If that happens, then it starts behaving like a metal, and Fermi level is very, very close to valence or conduction band within the limit of 3 kT, and this semiconductor is called as a degenerate semiconductor, which is like a metal. So, these are again two different terminologies. Normally for a semiconductor, we would like to operate within the range of non-degenerate semiconductor. So, in summary, we have looked at the electrical conductivity of semiconductor is electrical conductivity is given by this term Ne E mu E and Nh E mu P. This is your current density, this is your electric field, and conductivity is proportional to Ne and Nh, and for an intrinsic semiconductor it goes exponentially because Ne and Nh as a function of temperature, because Ne and Nh also change exponentially as a function of temperature, but it is different for extrinsic semiconductor, as we will see in the next class. Mobility on the other hand is same E tau divided by m, and this again decreases with temperature, but influence of temperature on conductivity is much higher for intrinsic semiconductor. For intrinsic semiconductor we can see we calculated the electron and hole concentration, and we must always remember that Np is equal to Ni square. For extrinsic semiconductor on the other hand, although Np is equal to Ni square, for a N type semiconductor N is equal to Nd, that is Ne is equal to Nd, and for a P type Nh is equal to Na. And for a N type semiconductor, in that case, using this equality of Np is equal to Ni square or Nh is equal to Ni square, we can write Nh to be equal to Ni square divided by Nd, and Ne is equal to Ni square divided by Na. So, these are the relations that we looked at, and we also saw that when you start doping them, the Fermi level shifts up for the N type, goes closer to the conduction band, and it shifts down for P type, goes closer to the valence band, but it must remain within the limit of Ec minus 3 kT and Ev plus 3 kT range, so that it remains like a non-degenerate semiconductor. So, we will stop here, and we will take this discussion on semiconductors, especially now we know extrinsic semiconductor, in the next class, especially in terms of motion of carriers and how they move inside the semiconductor. Okay, thank you.